The time is around 10 p.m. on April 20th, 2010. We're about 41 miles off the southern coast of Louisiana in the Gulf of Mexico. Something disastrous is about to happen. An explosion on the Deepwater Horizon drilling platform. The explosion and fire ended up killing 11 workers, but that's not where the destruction ended. It led to the world's largest ecological disaster. Over 500 million liters of one valuable substance spewed out of the ground over the course of 87 days, causing irreparable damage to the ecosystem, all for one special chemical. That leads us to the next question. Have you ever wondered what the most influential chemical is? Arguably besides water, it's the substance I hold in my hand. This liquid is not just valuable to the modern world, it's a global game changer. Wars have been fought over it, governments have fallen because of not having it, and you and I are both using products made from it. It's a natural resource that powers the modern world, yet we're running out of it. You read the title of the video, so you know it's crude oil. This black gold is one of the most sought after resources on the planet. Fortunes have been made and lost looking for it. Take Saudi Aramco, for example. It's the sixth largest company in the world with a market cap of $1.8 trillion, all thanks to oil. Back in 2023, the company had a revenue of about $500 billion, which is over a quarter of the entire GDP of Saudi Arabia. Oil production and activities contribute around 31.2% of the entire GDP of the whole entire country of Saudi Arabia. Going to the other side of the world, this year oil production hit a record high in the United States, in April at over 13,000 barrels of oil on daily average. This means over 500,000 gallons of oil pumped out of the ground on a day. That's more than an Olympic-sized swimming pool. Oil production and activities only make up around 8% of the total GDP of the United States, but it fuels the massive economy of the United States at over $27.36 trillion. It's no wonder why oil is worth so much when you consider the sheer variety of products that can be derived from it. Gasoline, diesel, fuel oil, lubricating oil, jet fuel, clothing, carpet, fertilizers, plastics, and even pharmaceuticals. This list is just the tip of the iceberg. It's nearly impossible to go to a day without coming into contact with a petroleum product. Well, given that 80% of the population has microplastics in their bodies somewhere. But that's just a different story. So the question is, how do we go from a liquid deep underground to all these products? That's what we're here today to explore. We see how oil is processed, the methods used, and see exactly what chemicals make up crude oil in this billion-dollar process. To start, we have to go back. The whole oil journey began millions of years ago when the process of oil formation started. Marine organisms such as plankton and algae perished and settled to the bottom of seabeds of ancient oceans. These ancient origins of crude oil is a testament to the long process of its formation. As time elapsed, this organic matter became trapped beneath layers and layers of rock and sediment. The intense heat and pressure generated by the layers and layers of material crushing down on the dead organisms caused it to transform the organic material into a dense, sticky liquid substance known as crude oil. Now that brings us to the present day. The human journey of crude oil begins with scientific process of exploration and drilling. Geologists, armed with a variety of techniques such as seismic surveys, play a pivotal role in identifying potential oil reservoirs, hidden deep beneath the Earth's surfaces. Their work is crucial in the entire process. Once a promising site is located, drilling rigs are set up to penetrate deep into the ground, often reaching the depths of several miles. When oil is discovered, it's drawn up through these wells and brought to the surface for further processing. The crude oil is then transferred via ships, trucks, trains, and pipelines to its processing locations known as refineries. The finding and extraction of the oil is a challenging part of oil refinery, but the real challenge lies in what crude oil is. It's a remarkably complex mixture of organic compounds such as methane, you know as natural gas, propane used for grills, alkanes, alkenes, and aromatic compounds. Thousands and thousands of compounds are found in oil, making its separation a true testament of human ingenuity. So how do we tackle the complexity of crude oil, a mixture of thousands of organic compounds? The answer lies in a process that humans have known about for thousands of years: distillation. This method allows us to separate compounds based on their boiling point. As a general rule of thumb, the larger organic compounds are, the higher its boiling point. By leveraging this knowledge, we can effectively separate small molecules from larger ones. making the refining process more manageable. Also, compounds of the same boiling point generally have similar properties. To begin this process, I pour the crude oil into a 1-liter round bottom and add some boiling stones. These stones are added to the liquid to provide nucleation sites for forming bubbles, which helps prevent superheating and sudden boiling. I also added a stir bar to aid in the even distribution of heat during the heating process. Usually you don't want to add stir bars and boiling chips to the same reaction vessel, because they'll scratch the glass. But this is the last thing this flask will ever do.
Foreshadowing is a narrative device in which suggestions or warnings about events to come are dropped or planted.
Next, I connected the flask to a distillation setup. This setup looks a bit different from the ones we are accustomed to. That's because we're doing fractional distillation. The process of fractional distillation is fundamental. It's beneficial in the laboratory for separating complex mixtures, such as our crude oil, into which we can distill it into its various components, known as fraction. Each fraction contains groups of organics with similar boiling points. Once ready, we start heating the flask and stirring it and turning on the condensers. You might have noticed that I have 2 condensers in a row. These condensers play a crucial role in the distillation process by cooling the vaporized fractions, causing them to condense back into liquid form. Having 2 in a row like this makes sure that any gas condenses. The style of condenser that would be best here is the gram condenser, but I only have a large version of this, which won't work for our setup. As the temperature increased, some crude oil evaporates and rises through the column. The temperature gradient within the column is crucial, with the highest temperature at the bottom and progressively cooler temperatures towards the top. Based on their boiling points, this gradient allows different hydrocarbons to condense at various heights within the column. Material with higher boiling point than the column cannot reach the top before condensing and running back down into the flask. We have a column known as a Crude column, which I'm probably pronouncing wrong, but it's French, so who cares. The column is a glass tube with spikes that direct material back down and provide locations for condensation to take place. When crude oil is distilled on a larger scale, plate columns are used. With that style, the fractions can be continually removed from the column without needing to do anything special, like removing our flask. Crude oil distillation must be done in a ventilated area as hydrogen sulfide escapes during distillation. HS is a very unhealthy and toxic gas to breathe. As we heat, the first fraction to be collected at the top of the column, where the temperature is the lowest, is the lightest fraction, consisting mainly of gases such as methane, ethane, propane, and butane, which all have boiling points below 40 degrees Celsius. These gases are typically used as fuel and produce chemicals like ethylene and propylene. Due to their low boiling point, I cannot collect these. My setup can't condense such low boiling point gases, and it was unlikely to begin with that these were to be in my sample to start. As the column continues to heat, the following fraction to condense includes gasoline, a volatile liquid made up of hydrocarbons boiling between 40 degrees Celsius and 60 degrees Celsius, which powers our cars. In this range are compounds like benzene, which are known as aromatic compounds, and a mix of short-chain hydrocarbons like hexanes. Soon the column heats past 60 degrees Celsius. The following fraction to condense includes naphtha, a mix of volatile liquid hydrocarbons between the boiling points of 60 degrees Celsius and 180 degrees Celsius. Naphtha is essential in petroleum industry as a feedstock for making plastics. Naphtha is used commonly as lighter fluid. I had issues reaching past 100 degrees Celsius with this column, even after wrapping it with aluminum foil. You may be thinking just to turn up the heat of the heating mantle, and I did try that to a point. The problem is if you have a cold liquid with a lower boiling point dropping into a boiling liquid with a higher boiling point, that causes the lower boiling point liquid to boil suddenly. We call this explosive boiling, which having a hot, sticky, flammable liquid escape its glass container via explosions is on the list of stuff that I don't want to happen. In industry, vacuum can be used in the column to decrease vapor pressure, causing the distillates to boil at lower temperatures. I have no good way of controlling vacuum pressure accurately for long periods of time, so I'll stick to normal pressures, but this is one way to fix that problem. Adapting to the situation, I replaced the column with a shorter air-cooled condenser, which requires packing material such as copper mesh to facilitate condensing like the Crude column. This flexibility in problem solving is a crucial laboratory skill, one in which just doing projects can help build this skill set. Eventually, this shorter column began to cool too much, and I had to shorten it again. leaving the glassware adapters to act as a column. If I was doing more precise work, this wouldn't be the best due to the low surface area for high boiling point compounds to condense on, but it will be acceptable for our purposes. Once the column reached past 180 degrees Celsius, I switched out the flask and collected at the temperatures between 180 degrees Celsius and 220 degrees Celsius. This fraction is known as the kerosene fraction. Kerosene is used as jet fuel and heating oil, and my personal favorite, rocket fuel. After climbing past 220 degrees Celsius, I once again switched out the flask. The following fraction, diesel, condenses between 220 and 250 degrees Celsius. This fraction fuels diesel engines and heating systems. This fraction had the most material by far, so much so that the flask quickly filled up and I had to switch it out for another one. Soon the temperature rose past 250 degrees Celsius and I switched out the flask. These heavier fractions, which are used as lubricating oil and waxes, condense between the range of 250 degrees Celsius and 400 degrees Celsius. These fractions are used for making up motor oils, greases, and candles. Before it got past 300 degrees Celsius, sulfur started building up. Sulfur is a common component in crude oil. An exciting term in the industry is sour and sweet, which describes the sulfur content of crude oil. Sweet is when the oil contains little sulfur, and sour includes a lot of sulfur. The more sulfur that's in the oil, the more difficulties can arise, directly leading to higher cost of processing of sour crude. At this point, I stopped heating and allowed the distillation apparatus to cool. Finally, the heaviest fraction, the residue that is left at the bottom of the flask. This fraction, which does not vaporize under the conditions of distillation process, include bitumen, also referred to as asphalt. This fraction is mainly used in road construction. To a lesser extent, it's used in roofing and other various applications. It has a very characteristic smell. If you've ever been by road construction, it's that warm road smell. After distillation is complete, we are left with 6 flasks of product. You can see that as the distillate temperature increases, it has a color gradient, starting with A being nearly transparent and F being red. The red color of the high distillate is most likely due to the presence of sulfur-containing compounds. We have successfully separated the organics by boiling point, but what does each flask contain? We know it's organic compounds, but what organic compounds? Okay, so this section might seem a bit dry, but it's actually quite fun once we get into it. If you're doing chemistry in any genuine way, you need to know how to analyze your samples. Without it, you're doing guesswork. Sample analysis can be as simple as seeing what temperature your sample melts at, all the way to as complicated as growing crystals and shooting X-rays at it. In the field of chemistry, we rely on analytical instruments to reveal molecules that are present. While there are several powerful options such as IR for functional groups and NMR for structure, these don't come close to where GCMS stands out as the ultimate tool for identifying and quantifying compounds, with unparalleled precision and sensitivity. Gas chromatography, mass spectroscopy, or GCMS for short, is the superhero of the analytical chemistry world. This technique, a fusion of gas-liquid chromatography and mass spectroscopy, is particularly well suited for identifying our organic compounds. However, we must exercise caution to avoid introducing anything that can disrupt the instrument and break it, such as large sulfur compounds. These can clog up the instrument, so we must prepare our samples first to remove these sulfur compounds. Before we do that, let's run a quick NMR on our sample, and it shows us what structures to expect to see with the GCMS. There are 2 massive peaks. These are aliphatic CH2s and aliphatic CH3 peaks. So we'll see compounds like these. Also, a trailing effect off those peaks means that we'll have aliphatic CH compounds, like these. Also, a peak around 7-ish, which means we'll expect to see some ringed compounds like this. How fun! Okay, let's go back to GCMS now. Preparation of samples is a crucial step in our process. I accomplish this by taking a few milliliters of the distillate and adding it to a 50 milliliter Erlenmeyer flask. I then introduce a concentrated solution of sodium hydroxide. The hydroxide reacts with the sulfur compounds, rendering them water soluble and removing them from the distillate. I repeated this for all three of the reddish samples, and after allowing them to react, periodically swirling them for approximately 20 minutes, I added water to each flask to make it easier to facilitate the removal of the clean distillates. Using a pasture pipette, I transferred each sample into their respective vials. This makes it very easy to see the color gradient, with clear colorless distillate like A and a completely dark brown opaque distillate F. I then added molecular sieves to each vial to eliminate any water that might be present in our sample. The dry and clean distillates are then transferred to GCMS vials. The beauty of GCMS lies in its ability to use minimal sample amounts for data collection. If you can see your chemical in the vial, you have enough for analysis. After adding each sample, I carefully fill the vials with some dichloromethane, which dissolves the distillates. The DCM acts as a carrier that will carry our analytes to the instrument for analysis. These vials are then loaded into an autosampler, automatically injecting samples as the test runs. Before we begin running the samples, we must set up the software. The most important aspect is the method we use to run the samples. With a proper technique, we'll get good data, primarily focusing on temperature control. When the sample enters the chromatography part of the instrument, the sample is vaporized and carried by an inert gas through a column with a stationary phase. As different compounds travel through the column at different rates, they separate based on their chemical properties. Other compounds have different boiling points, so we do a temp ramp for this column, which then causes certain chemicals to leave the column as they boil off at certain temperatures. In this method, we heat the column to 42 degrees Celsius and hold it there for 2 minutes. This is to remove any DCM from the samples before testing. Because if there's a lot of DCM, turning on the detector right away will overwhelm it and cause it to break. By boiling off all of it before we start analyzing the samples, we avoid analyzing that and only analyze the sample that we want to analyze. Then we slowly ramp up to the max temperature and hold it there for a few minutes to ensure all material moves through the column. With our method developed, all we need to do now is label our samples and their data outputs and start the instrument. Once the instrument has warmed up to the proper temperature, the autosampler begins its role. It washes the syringe with the methanol a few times before picking up our sample and injecting it. This automated process ensures that our samples are handled precisely and consistently, reducing the potential for human error in analysis. Skipping past the point of solvent cutoff, we start to get data output as a chromatograph. We already discussed the GC part of the GCMS, but the MS is where the magic happens. After separation, the compounds enter the mass spectrometer, the MS phase, where they're ionized and broken down into fragments. The mass spectrometer then measures the mass-to-charge ratio of these fragments, producing a unique spectral fingerprint for each compound. This dual capacity makes GCMS incredibly precise and essential for identifying complex mixtures, like our crude oil distillates. The chromatogram captures data in terms of time and peak intensity. The beauty of this process is that it's largely hands-off. Each sample takes around 30 minutes to run, so after about 3 hours, all the data is ready for analysis. Next, we open up a second software for post-run analysis. Let's dive into sample C for a bit of fun. Each peak in the chromatograph represents a specific chemical. By subtracting background noise from the peak area, we isolate a selected peak. We then use a similarity search tool to identify the compounds based on their mass fragmentation pattern, and voila! We discovered 2,6,10-trimethyl pentadecane. The software provides a percentage indicating how likely the fragments are to a matched known sample. We aim for samples with a similarity score above 90 to 95%, while anything below 80% is probably not a match. Now, doing this manually for each peak isn't exactly thrilling, so let's have the computer handle it for us. We start by peak integration, setting the slope value to a high number like around 1,000. This way, we focus on significant peaks while ignoring all the small ones, filtering out instrument noise and faint signals. Once everything is set, we initiate the auto search. Which when it finishes, we generate a report in a PDF format. Listing all 92 detected peaks. A key column to note is the area percentage, which shows the proportion of each chemical in the composition that we analyzed. I repeat this process for the remaining 5 samples. Altogether, we detected 339 chemicals, with some overlap between samples, of course, as certain chemicals likely appear in multiple distillates. While there may be thousands of chemicals found in crude oil, our samples are quite small, which means that in some cases there's only going to be a few molecules of each chemical present, which our instrument is not sensitive enough to detect those, so those get ignored. And we also filtered out all the short compounds that were barely detected, which leads us to the 339 number, which is quite accurate for the main majority of the chemicals there, but we are missing a ton of chemicals that are just too faint for our instrument to detect. Analyzing the chromatographs reveals some fascinating trends. In sample A, for instance, all the peaks cluster on one side, indicating low boiling point compounds. This distillate is rich in aromatic compounds like toluene and ethylbenzene, with methyl cyclohexane, a low boiling point ringed compound, dominating the composition. The same pattern appears in distillate B, but with a mix of aromatic compounds and longer chain organics like 4-methyldecane. Distillate C shifts the focus to the middle of the chromatograph, showing mostly chained compounds made out of carbon, like undecane and hexadecane, with a few ringed compounds mixed in. Both D distillates share similar composition, which is expected. It's cool to see the more bigger rule in action here. As compound size increases, so does boiling point. In the final distillate, F, we see only chained carbon compounds, with the largest being heniacasane, a 21 carbon chain. And now you know how to process oil. Go out and find some oil. Thanks for watching.